Hey everyone, it's Bradley Bush with another algebra video for you. Today we're talking about rationalizing denominators. I'm glad you're with us today. If this is your first time to the channel, thank you so much for coming. I'd love if you would leave some comments, like the video, or subscribe to the channel. Let's get going. So rationalizing denominators. We rationalize denominators to get rid of the radicals in denominators. So rationalizing a denominator is just a phrase we use in math to describe the process of getting rid of a radical in a denominator. We do this by multiplying the numerator and the denominator by the smallest number that will give us a perfect square in the denominator. So this is kind of an important part, so let me state that again. We rationalize the denominator by multiplying the numerator and the denominator by the smallest number that will give us a perfect square in the denominator. Let's do some examples to help you see what I'm saying. And once you see it, I think it'll be, you won't think it's as bad as it may sound. So let's look at the denominator on a first. So a here we have 3 over root 8, or square root of 8. We need 8 to become a perfect square. Because if we take the square root of 8 right now, we don't get a perfect square. So a perfect square is something like 16. The square root of 16 is 4. 16 is a perfect square because 4 times 4, or 4 squared, is 16. So what's the smallest thing we can make 8 into that's a perfect square? Well, 8 times 1 is 8. 8 times 2 is 16. 16 is a perfect square. So let's multiply top and bottom by root 2. Why do we multiply top and bottom by root 2? We understand the root 2 part now because 2 times 8 gives us 16, and that gives us a perfect square. But why do we have to do it to the top? Well, the reason is we don't want to change the value of our expression. If we plugged 3 over root 8 into our calculator, we'd get a number. And we don't want to change that number. We just want to get rid of the radical on the bottom. So we want to rewrite it into an equivalent form that doesn't have a radical on the bottom. So we know that every time we multiply by 1, anything times 1 is itself. It doesn't change. So there we go. What is root 2 over 2? It's the same thing as 1. That is exactly equal to 1. So we're just multiplying 3 over root 8 by 1. And so we're not changing the value, but as we'll see in a second, we're getting rid of the radical in the bottom. So let's keep going. Root 8 and root 2, they both have the same index, which is 2 on the square root, so we can multiply the 8 to 2 and give us 16. So we get 16, root 16 in the bottom, and we get 3 times root 2 in the top. Root 16 in the bottom gives us 4. So we get 3 root 2 in the top and 4 in the bottom. And notice we no longer have a radical. And if we plugged in 3 times root 2 over 4 into the calculator, we would get the same thing as if we plugged in 3 over root 8. So we're done. We've rewritten it in a different form, but it's equivalent. It has the same numeric value as our original expression. So that's rationalizing a denominator. So out of just curiosity, this is a side note, why don't we want a radical in the bottom? Turns out it's kind of a lame reason. And I say lame because a while back it was legitimate, but today it's not really that big of a deal. So we don't like radicals in the bottom because when you're doing a long division problem, and you have a radical on the bottom, it makes your long division problem really, really tedious and hard to do. But if you don't have a big number in the bottom, or a crazy number in the bottom, then the long division is much easier. So back in the day before they had calculators, they would rationalize the denominator because it would make their long division easier. But today we just throw it into a calculator and we don't really care. So mathematically speaking, there really isn't a reason to rationalize your denominator most of the time. It's just become convention that the simplified form it doesn't have a radical on the bottom. There's your side note for the day. Let's do B. So we have the cube root of 3. Cube root of 3. So cube root, that means we have to have something multiplied by itself 3 times. What's the smallest thing we can change 3 into? Let's say perfect cube. Well, probably 27, right? 3 times 3 times 3. So we have 1 3 already. So we need 2 more. So 3 squared is the same thing as 9. So if we multiply by the cube root of 9, top and bottom, and again we're just multiplying by 1, and we choose the 9 because the 9 times the 3 gives us, well, we have 2 and then 3 root of 9 at the top. We have the cube root of 3 and the cube root of 9. That gives us the cube root of 3 times 9, which is 27. Let's keep writing here just so you can see all the steps. Cube root of 27. What is the cube root of 27? 3. So now we have 2 times the cube root of 9 all over 3. And we're done. No more radical on the bottom. How about this next one? We have an 8 and we have a 4th root. Let's see, so we need to make 8 into something that is raised to the 4th power. Well, 8 times 1 is 8. 8 is not something raised to the 4th power. 8 times 2 is 16. 16 is something raised to the 4th power. So let's do 4th root of 2 over 4th root of 2. And what does that give us? So 2 times 8 is 16. 4th root of 16. And we have 18 times 4th root of 2. What is 4th root of 16? 16, by the way, is the same thing as 2 to the 4th power. And the 4's cancel and the 2 comes out. So this is wonderful, right? So we get 2 in the bottom. We have 18 in the top. 4th root of 2. And we can do some simplification. And this leaves us with our answer, which is 9 times the 4th root of 2. Sweet. Questions? Please put them in the comments. I'd love to hear what you guys think. Also, I'd love to hear what you think about the reason that we rationalize denominators, and why it's not so needed today. But we still do it because I guess we're creatures of habit. All right, multiplying conjugates. Sometimes we rationalize the denominator by multiplying the numerator and the denominator by the conjugate of the denominator. We do this when we have denominators that have 2 terms, and you'll see those. We can't just multiply by a single value because we have 2 terms, and the 2 terms with a minus or plus in between restrict us from just doing what we did above. So the way we do something that has the same effect, meaning getting rid of all of the radicals in the denominator, we do this process called multiplying by a conjugate. So what is a conjugate? Conjugate is something that's super easy to find. If you're given a phrase or an expression, a plus b, you find the conjugate just by changing the sign of the second term. So this plus changes to minus. That's it. So you take the second term, which is the b, you change its sign, and that's the conjugate. So if we have x plus root 2, and we want to find the conjugate would be the first term stays the same, the second term changes sign. So it was positive, now it becomes negative. So the conjugate of x plus root 2 would be x minus root 2. We like conjugates because when we multiply them together, cool things happen. And we get the result we want, meaning we no longer have radicals. Here's a shortcut formula for what happens. If you're multiplying two conjugates, the end result is you square the first term, you square the second term, you've got a negative in between, and you're good to go. If all of the terms everywhere in your product are in radicals and they all have the same index, then it even works out even better. So let's do an example. We have root x plus root 2. That's in the first parenthesis. The second parenthesis is root x minus root 2. So we have, we're multiplying root x plus root 2 by its conjugate, which is root x minus root 2. Let's just do the FOIL here and see what happens. So when we're multiplying this out, we'll multiply the first term, right? The first term gives us root x times root x. Now the outside is root x times negative root 2. And the inside gives us root 2. Let me change the direction of that parenthesis. Root 2 and root x. And then we have the last. Let's do purple. This is just normal multiplication here of two terms that both have two terms in them. So we get root 2 and negative root 2. When we do that multiplication, we end up getting, I'm going to bring this up top, we have root x squared from the first term. The second term, the O, we have negative. Actually, check this out. We don't even need to write that down because look what happens. This term and the second term are exactly the same, but they are opposites in sign. The first one is negative root 2x, and the second one is positive root 2x. They cancel each other out. It's like 1 minus 1, 0. They're both gone. That's part of why we like conjugates, because the middle two terms drop out, always. And the first term and the last term, they're just squared. So if we have a square root, that squaring gets rid of the radicals in those two. So I'm not even going to write down those middle two terms. The last one would be, we'll have our negative there from the second root 2. And we have root 2 quantity squared. This gives us the square root of x squared. Just gives us x. Square root of 2 squared gives us 2. And we get x minus 2, which is exactly what we said we were going to get here in our formula. And notice we no longer have radicals. We started with a bunch of radicals. In each of these terms we had a radical, and we ended no radicals. So we like rationalizing this way because it gets rid of all the radicals. Let's try a couple examples where you can see. Notice both of these examples we have, in the bottom we have root 3. In the first one, the second one we have root 5. So we have radicals in both of them. We don't want the radicals. We have more than one term, so we've got to use this new method of multiplying by a conjugate. The conjugate in A, so in A we have 7, it's a fraction, we have 7 in the top and 5 plus root 3 in the bottom. So our conjugate is 5 minus root 3, and again we're multiplying by 1, so we have to multiply top and bottom by the same thing. We get, in the top we have 7 times 5, which is 35. and then 7 times negative root 3, which is negative 7 root 3. And in the bottom, what do we have? We have 5 and 5, which is 25. We have root 3 and 5, which is 5 root 3. And then on the outside, we have the negative of that, 5 root 3. And then we have root 3 and root 3, which is negative root 3 squared. Let's do a little more simplification, and we'll be done. These two terms in the middle cancel. Root 3 squared is just 3. So we have 25 minus 3, which is 22. So we have 35 minus 7 root 3 over 22. And that's it. Let's try our second one. So our second one, we have 8 in the top and 4 plus root 5 in the bottom, and we're trying to rationalize the denominator. So again, we've got to multiply by the conjugate in the top and the bottom. So we have 4 minus root 5 in the top and the bottom. Let's multiply the 8 through, so we get 8 times 4, which is 32. 8 times negative root 5, which is negative 8 root 5. In the bottom, we're just foiling this again. We have 16, 4 times 4 is 16, and then we have negative 4 root 5 plus positive 4 root 5 and negative root 5 squared. Lucky for us, again, the middle two terms cancel. Root 5 squared is just 5. So we get 32 minus 8 root 5 in the top. In the bottom, we have 16 minus 5, which is 11. And we're done. Thank you so much for watching. Hope you have a great day.